Okay, these are notes for 4-2. We're going to start to talk about degrees and radians. Radians are just going to be a new concept for you guys. So hopefully we can make it make sense. All right, so angles and their measures. We're going to go back to geometry. In the days of geometry, you learned that an angle was comprised of two non-collinear rays that share a common endpoint. That's how they defined an angle for you, and that common endpoint was known as a vertex. Okay, so an angle can be formed, if you think about it, by rotating a ray around its endpoint. And when a ray is rotated about its endpoint, the starting position forms the initial side of the angle. So if you look over here to the right, we have this initial side, which is the positive x-axis, and this angle has a vertex at the origin. That's going to be what we see every single time. The ending position of the ray after it rotates forms the terminal side of the angle. Terminal means to finish, so the terminal side is where the angle stops rotating. Okay? So an angle is in standard position if it has a vertex at the origin, and that's what we're going to be focused on, vertex at the origin, and the initial side is along the positive x-axis always. So this angle over here is standard position. This is the positive x-axis, vertex at the origin. And what we want to think about is creating this angle from rotating the initial side back towards the terminal side. So the measure of an angle, what really is it? It is the amount and direction of rotation that we need to move from the initial side to the terminal side of the angle. So it's how much and in what direction. So what we're going to be exposed to today is the fact that we can have negative angles, and that means they're going to change the direction of rotation. So first up, a positive angle is what you would generally think of when you picture this angle rotating. It's going to be generated by a counterclockwise rotation, just like you see in the picture above. So going against the clock in that direction. A negative angle is a clockwise rotation. So let's look at these examples down below. On the left, we have a positive angle, and we can see from the initial side, positive x-axis starting at the origin, we rotate counterclockwise, and we go all the way over here into the third quadrant. So the terminal side is over here. So this may be an angle of, halfway around the circle is 180 degrees, maybe plus another 10 or 15. So that total angle may be 190, 195 degrees, somewhere around there. Then we have a negative angle. So now this is something new. We can start at the same initial side, the positive x-axis, vertex is at the origin, and we're going to go clockwise in this direction, back around the other way, and this one ends up in the second quadrant. There's my terminal side in the second quadrant. So now my angle is maybe this 180 degrees and then maybe another 60 degrees. So that may be an angle of negative 240 if we maybe had to guess. So there's a difference between positive and negative angles. It is the difference in the way we rotate. So we're going to practice and draw a few sketches of the following angles in standard positions on the graphs below. So the first one, to be in standard position, again, we're going to start at the positive x-axis right here. So A says we want a positive angle less than 1 revolution, so less than 1 full circle around, and the terminal side in quadrant 3. Now, since they refer to quadrants, we're going to just revisit and make sure we know where our quadrants are. This is quadrant 1, quadrant 2, 3, and 4, and that should be familiar to you. So, as we draw this angle, we put our pencil tip on the initial side and we start to rotate. We're not going to go all the way around, and we want to end up in quadrant 3. So somewhere in quadrant 3, anywhere in quadrant 3. So I'm going to stop right there and I'm going to draw the terminal side. And there's my angle. So the angle that we're talking about is this right here. Okay. Letter B says a positive angle between 1 and 2 revolutions. So more than one full circle around, but not quite 2 revolutions. And we want the terminal side in quadrant 1. So we want to end somewhere in here. So we're going to start on the initial side, positive x-axis, and we're going to rotate counterclockwise. We're going to go all the way around once. And then we begin a second revolution, but we stop somewhere in the first quadrant. And then we're going to draw our terminal side from the origin, from the vertex. And there's my angle. So what may look like an acute angle is actually larger than 360 degrees. We've gone all the way around 360 and then maybe another 60. This may be a 420 degree angle, even though it only looks like maybe a 60 degree angle. We have to keep in mind that we have multiple revolutions. All right, letter C. Now we want a negative angle. So we're going to start on the initial side. Negative angle, so we're going to go clockwise between 2 and 3 revolutions, and the terminal side we want down here in the 4th quadrant. So we put our pencil tip on the initial side. We go clockwise. We want a negative angle. So we're going to go around once, twice. So between 2 and 3 revolutions, we're not going to go another full revolution. We're on our 3rd revolution around, but they want us to stop in the 4th quadrant. So there I am. There's my terminal side. So what may look like, again, an acute angle, that has 2 full revolutions. That has 720 degrees at least, and then some more. So even though it looks like an acute angle, because of the multiple revolutions, it's much more than that. And the last one, we want a negative angle, less than 1 revolution, terminal side on the negative y-axis. So here's my initial side, and there's the negative y-axis down below the x-axis. So if we rotate in a negative direction, we're going to stop right there, and my terminal side will be on the negative y-axis. Okay, so hopefully now we understand the difference between a positive angle and a negative angle. And we now have the idea that we can rotate around this circle multiple times, still maintaining the center at the origin, where our vertex is, and we now know the difference between the initial side and the terminal side. Okay, now we're going to label our unit circle. Everyone hears a lot about the unit circle. So here we go. This is our unit circle, and we don't know anything about radians yet, so we are going to label it in degrees. So first we're going to do degree measures for 1 full revolution of the circle below. Now there's lots of different ways you can break this down and do this, but I'm going to break this down into 90 degree angles, then 45s, then 30s and 60s. Those are our special angles that we're going to focus a lot on, the 30s, the 60s, the 45s, and the 90s, the quadrantal angles. Okay, so we start at the end of the initial side right over here. So we're going to picture this as our initial side, and before we rotate it all, we have 0 degrees. Now I'm going to go every 90 degrees around the circle. So as I rotate, 90 degrees is up here, the positive y-axis. Another 90, I'm over here at the far left. 180 degrees. Okay. Then another 90 degrees will be 270 degrees. And another 90 degrees will be 360 degrees. Back at what looks like the initial side. And we've got 1 full revolution. So 1 revolution is 360 degrees. Now we're going to split those quadrants up, and I'm going to go by 45s around the circle. So from 0, I'm going to cut the quadrant in half. There's my 45 degrees. Another 45 puts me at 90. Another 45 puts me at 135, bisecting the second quadrant. Another 45 puts me at 180. 45 more puts me at 225. Another 45 is 270. Another 45 is 315. And 45 more puts me at 360. So now I've done my 45s all the way around. The last special angles that we're going to do are my 30s and 60s. Now 60 is a multiple of 30, so all we need to do is go 30 around, and that covers the 60s as well. All right, so from 0, we have 30 degrees here. 30 more gives me 60. Another 30 gives me 90. 30 more gives me 120. Another 30 gives me 150. Plus 30 is 180. Plus 30 is 210. Plus 30 is 240. Plus 30 is 270. Plus 30 is 300. Plus 30 is 330. And then plus 30 is back at 360. So here are the degree measures all the way around the unit circle in all 4 quadrants. Okay, so now that we've talked about degrees, we're going to move on to what we've all heard about, radians. So let's start off by looking at what measuring in radians really means versus degrees. So measuring angles in degrees is very useful in applications like surveying, navigation, involving triangles. But degrees have no relationship to linear measurement. So to look at different measures of angles for this chapter, in the rest of it, in a good bit of it, we're going to focus on radians. So what is a radian? Back in geometry, when you looked at circles, you learned that you had arc lengths and you had radius, and then you would have these central angles, where the central angle was equal to the arc length. Well, we're going to look at that relationship again, but now we're going to look at something called radian measure. And here's what it is. So the measure theta in radians of a central angle of a circle is equal to this. It is the ratio of the length of the arc, which is S, to the radius of the circle, which is R. So from this diagram, we could represent theta as S over R. And theta is now measured in radians. It is a ratio of the arc length to the radius when you have an angle that is in the center of the circle. Okay, so as long as the arc length, let's look at some of these points here. As long as the arc length S and the radius are measured using the same linear units, the ratio S over R is unitless. So here's what this means for us. We don't have to write the word radians every time. We will, here we go, assume all angles are measured in radians unless we see the degree symbol. So the degree symbol is now going to be very important. It's going to distinguish whether or not we're talking about degrees or radians. So while most of the time radian angle measures will be written in terms of pi, that's not always the case. So remember, angles are only measured in degrees if the degree symbol is used. So that's something that we're going to have to practice and get used to. Okay, so let's see where we get some other relationships. The formula for the circumference of a circle. We know that it can be circumference equals pi d, but we're going to look at circumference equaling 2 pi r. So that represents the entire circumference around the whole circle, 2 pi r. So if we use the formula from above, meaning theta is equal to S over r, to draw a conclusion about the central angle of a circle, here's what we have. We know that theta, that central angle, is arc length over radius. So the arc length all the way around a circle is 2 pi r divided by, or to the ratio of the radius. The r's cancel out, so theta is equal to 2 pi. So the central angle of a circle is equal to 360 degrees or 2 pi radians. So this 2 pi represents 1 revolution around the circle. Okay? So let's take a look at some examples. Here are examples of radian measure within a circle, and these are going to be important. Just like we learned the degrees around a circle, we're going to need to know the radians. So the first one full rotation is 2 pi r divided by r. So 1 full revolution is 2 pi radians all the way around. And you can see that this is darkened all the way around. So if we want half the circle, we're going to take half of 2 pi, and the 2's would cancel, and we just have pi radians. So half a circle is pi radians. A fourth of a rotation will be 1/4 of 2 pi. So those cancel, and the 4 becomes a 2, pi over 2 radians. So this would be pi over 2 radians, would be our theta and our arc length. And then a sixth of the rotation. So 1/6 of 2 pi. Those would cancel, and we would have pi over 3 radians. Okay, so now we're going to go back and we're going to label the radian measures for 1 revolution of the circle on the previous page. Now, I'm going to break it down just like I did with degree measures. Okay. So if we go back, and now we're going to talk in degrees. So 0 degrees is the same as 0 radians. Then 90 degrees, a fourth of the way around, is pi over 2. So now I'm going to go around, just like we went around in increments of 90, I'm going to go around in increments of pi over 2. So 90 is pi over 2. Over here, I would have 2 pi over 2, which is pi. Down here, I would have 3 pi's over 2. And back around, I would have 4 pi's over 2, which is 2 pi. So there are my quadrant radian measures. Then I'm going to do the 45s. So 45 degrees would be pi over 4. If we take the 90 degrees and we cut that in half, I'm going to do this kind of off to the side here just a minute. If I take half of 90, that's like taking half of pi over 2. That's pi over 4. So that's my 45 degree measure. So 45 is pi over 4. So now I'm going to go around the circle in increments of pi over 4, just like I went around the circle in increments of pi over 2. Now I'm counting by pi over 4. All right, so watch closely. You might want to watch this one time and then go back and watch it again while you're trying to write them in. So I start with 0. Pi over 4 is at 45. Another pi over 4 is here. Now watch this. 2 pi over 4. That's pi over 2, and I already have that labeled. Then another 45 is 3 pi over 4. Another 45 is 4 pi over 4. Well, that's already labeled. That's still pi. Another pi over 4 is 5 pi over 4. Another pi over 4 is 6 pi over 4, which reduces to 3 pi over 2. We've already got that. Another pi over 4 is 7 pi over 4. And another pi over 4 is 8 pi over 4, which reduces to 2 pi. So again, going around the circle, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. And the ones that reduce, of course, we simplify those down. Don't leave 6 pi over 4 like that. We want to reduce it to 3 pi over 2. Okay, when we did degrees, the last thing we did was we went around by 30s. So that's a third of 90 degrees. So if we take a look 90 degrees we know is, again, I'm going to go over here, 90 degrees is pi over 2. So if I want a third of that, that's pi over 6. So now I'm going to go in increments of pi over 6, and I'm going to count by pi over 6's. So I start with 30. There's pi over 6, 2 pi over 6, which reduces to pi over 3. Then we have 3 pi over 6, which reduces to pi over 2. Already have that. Then we have, after 3 pi over 6, we have 4 pi over 6. We're going to reduce that to 2 pi over 3. Then 5 pi over 6, which does not reduce. Then 6 pi over 6, which we already know is pi. Then we have 7 pi over 6. Then we have 8 pi over 6. That's going to reduce to 4 pi over 3. Then we have 9 pi over 6, which is, again, 3 pi over 2. Then we have 10 pi over 6, which is 5 pi over 3. Then we have 11 pi over 6, which does not reduce. And then we have 12 pi over 6, which once again is 2 pi. So I hope that doesn't get too crazy busy. I wanted to show that, you can count, you can do these very easily by just counting by those increments, but then you absolutely have to reduce those fractions. Okay, so here is your unit circle with degrees and radians. And again, I know that at some of them we have 2, like for example right here we've got 2 pi over 6, but that is pi over 3, so those are one or the same. Okay, so now that we've done that, we're going to go on and look how to go back and forth between degrees and radians, how to convert. So degree and radian conversion rules. We've already established that 360 degrees is the same as 2 pi radians. So how do we convert any degree measure into radians? Well, I want you to think back. I'm going to go off to the side here just a little bit in a little bubble. So just take a minute and go back with me to Algebra 1, middle school, and think about how we would convert let's say 14 inches to feet. So if I want to convert 14 inches to how many feet, I would multiply by a unit conversion where I would have the same amount represented in the numerator and denominator, but they would be in different units. So I know that there are 12 inches in every 1 foot. So when I want to convert inches, I want to make sure when I write this unit conversion, right, that we put the inches on the bottom and the feet on the top. So 1 foot and 12 inches. They're the same amount, but this helps me convert from one unit of measurement to another. So inches are going to cancel, and I'm left with feet. And now I have 14 over 12, which I can reduce to 7/6 of a foot, or 1 1/6 feet. So we're going to use the same concept to convert degrees to radians. And I can erase this that was just to kind of help explain why we're going to do what we do here. So if I want to convert a degree measure into radians, I'm going to multiply by pi over 180 degrees. Those represent the same amount. Pi is halfway around the circle, and so is 180 degrees. So for example, if I have a 20-degree angle and I want to convert this to radians, I'm going to multiply by a unit conversion, or a unit factor, where the amount is the same in the top and the bottom, but different units. Because I want degrees to cancel, I'm going to put the 180 in the bottom and pi radians in the top. This will make my degrees cancel, and I'm left with pi, and then 20 goes into 18, 9 times. So that would be pi over 9 radians. Hopefully that makes sense. We're going to have a chance to practice here in just a minute. Then to go the other way, to convert a radian measure into degrees, we're going to do the opposite and multiply it by 180 degrees over pi. Okay? So for example, if I want to convert pi over 2 to something in degrees, I'm going to multiply by something that gets, I want the pi's to cancel, because that will cancel. Essentially, that's my indication that I'm in radians. So I want pi's to cancel. So I'm going to multiply by 180 over pi. So the pi's will cancel. 2 goes into 180 90 times, and that's 90 degrees. And we know that pi over 2 is now the same as 90 degrees. Okay. So now let's do some more examples, knowing what we know. We want to write each degree measure in radians as a multiple of pi, and each radian measure in degrees. So we're going to look at 120 degrees. I want to multiply this by pi over 180 so that my degrees will cancel. My 120 and my 80 cancel. I can look at that as 12 and 18. I'm still going to have my pi, and then reduce that fraction, 12 and 16. 6 goes into 12 twice and into 18 3 times. So 2 pi over 3 is the same as 120 degrees. Let's look at B. I have negative 45 degrees. So I will have a negative measurement in my radians, so I'll put that negative out there. And now just focus on getting degrees into radians. I want my 180 degrees on the bottom so that degrees will cancel, and pi on the top. So I'm left with pi in my numerator, and I have 45 over 180. 45 goes into 180 4 times. So that is pi over 4. So negative pi over 4 is the same as negative 45 degrees. Now we're going to convert radians into degrees. So I'm going to show you a couple of ways to do this, just because there's one way that's really easy, but the first way we're going to stick to the plan of using our conversion vectors. So 5 pi over 6, I want the pi's to cancel because that would cancel essentially my radian measure. We can think of it that way. So I want to multiply by 180 over pi. So pi's cancel. 6 goes into 180 30 times, and 5 times 30 is 150 degrees. Now the other way that you can do this is when you have radian measure, you can substitute 180 degrees for pi. You can do that. So I could have done 5 times 180 divided by 6. And again, that's going to give me 150 degrees. So that's maybe a quicker way to convert, but they both work. So D, negative 3 pi over 2. We are going to convert that to degrees, and it's going to be negative. And so if I want this to be degrees, I want the pi's to cancel, so I'm going to put pi on the bottom, 180 on top. Pi's cancel, 2 goes into 180 90 times, and 90 times 3 is 270. So a negative 270 degrees is the same as negative 3 pi over 2. Okay. So now that we've done some conversions, we're going to look at something called coterminal angles. Okay? So if you have co-captains on a basketball team or a football team, if you have, co-department chairs, that means you have more than one. So coterminal angles, they are going to share a terminal. See that? Co-terminal. These angles will share a terminal side. Okay, So how do we do that? This says by adding or subtracting revolutions, okay? And remember, revolutions can be thought of in radians as 2 pi or in degrees 360. Those are revolutions. You can add or subtract revolutions, or you can change direction. Any number of angles can have the same initial side and terminal side, but they will have different degree or radian measures, and these are called coterminal. So let's take a look at this example down here. So positive coterminal angles. Positive, notice they're both going counterclockwise in their rotation, so they're both positive. So let's say that alpha, if I can draw an alpha, let's say that that angle is 60 degrees. Let's just suppose that it's 60 degrees. Well, this angle beta has the same terminal side. However, you can see that it's gone around one full revolution plus the amount that alpha is. So I could say that beta is 360 plus another 60 degrees, which is our alpha. So beta would be 420 degrees. Different measurements, but they are coterminal because they share this terminal side. Okay, now we're going to look at positive and negative coterminal angles. So in the first one, they were both positive. Here we have a positive and a negative, but they share a side. So now let's look at alpha. Well, alpha looks like maybe it's gone 180, let's say plus 30 more. So let's say that alpha is a positive 210 degrees. Well, then if we look at beta, beta has gone in the negative direction and stopped at the same place. So beta would be what? Well, together they make a full revolution. So we would take 210 and subtract to find the difference in that revolution, subtract 360, and we get 150 degrees, negative 150 degrees. Now, you can also just take the difference by doing 360 minus 210 and getting 150, but you have to remember the angle was rotated clockwise, so don't forget to put the negative on there. So those are examples of coterminal angles. All right, let's define this just a little bit more and how to find multiple coterminal angles. So coterminal angles, first let's talk about in degree measure. So these two rules are both the exact same, but as you can see, one down here has 360 and one has 2 pi in it. So if alpha is the degree measure of an angle, then all angles measuring alpha plus 360 degrees, where n is an integer, are coterminal with alpha. So what n is, guys? N is an integer because it's the number of revolutions. So if we have alpha and we add another 360, we're right back at the same place. And another 360, back at the same place. And another 360, back at the same place. So they would all be coterminal, but as we keep adding 360, the degree measure changes. So in radians, the concept is the exact same. But in radians, if alpha is the radian measure, then all angles measuring alpha plus 2 pi n, where n is an integer, are coterminal with alpha. So all this says now is we would just, instead of adding 360 multiple times, is we would add 2 pi, the number of revolutions. That's my n value. Okay, so let's put this into practice. Example 3, identify all angles. So we want every angle that is coterminal with the given angle. Then we're going to find and draw one positive and one negative angle coterminal with the given. Okay, so 45 degrees. Let's draw this. 45 degrees is cutting that first quadrant in half. So there it is. Let's call this theta. So if I want to represent all the angles that are coterminal, all of them, that's infinite. We could spin that around in a circle infinitely many times. So to represent all of it, we would take 45 plus 360, because 45 is in degrees, we're going to use 360, times n. This represents all angles coterminal. Now, if they want one positive, well, let's give them one positive. We're going to do 45 plus 1 revolution. That would be 405 degrees. So we would start initial side, go all the way around 360, and one more. There's 405 degrees. Then if we want a negative, we're going to take 45 and subtract 360. So watch this. As we look at the diagram, I'm going to go from the 45 degrees and I'm going to subtract 360. So right there, I've taken 45, take 360 away, take 1 full revolution away, and where am I? I am at negative 315 degrees. What that means is from my initial side, watch right here, from my initial side, I would rotate 315 degrees around, and I would be coterminal with 45 degrees. Okay, now, angles with degrees are maybe a little easier to see because you're used to them, but now we're going to work with radians. And just hold on to the concept of adding and subtracting the 2 pi, just like we added and subtracted the 360. So if I have negative pi over 3, so that's going to be down here, negative pi over 3. There's my theta. So if I want all angles coterminal, that's going to be negative pi over 3 plus infinitely many revolutions, 2 pi n, or 2n pi, doesn't really matter. So this represents all angles coterminal. Now, if I want one positive, just like we did before, I'm going to add 2 pi. Now here's where adding and subtracting fractions becomes a necessity. You're going to have to get a common denominator. So if I'm looking at 2 pi, but I'm in thirds, I'm going to rewrite this as negative pi over 3 plus 6 pi over 3. That still represents 2 pi, but now I'm in thirds, and I can add them together. Negative pi over 3 plus 6 pi over 3 is 5 pi over 3. That's a positive coterminal angle in radians. If I want a negative coterminal angle, I am going to subtract 2 pi. So that's negative pi over 3. So I'm at negative pi over 3, and I'm going to subtract a full revolution around. So that's minus 6 pi over 3 again, which is negative 7 pi over 3. So 6 pi over 3, again, if we think about starting at the initial side, I'm going to go all the way around. That's 6 pi over 3, or 2 pi, and then another pi over 3 is negative 7 pi over 3. Okay, just a couple more. Now we're going to talk about something that still, again, very familiar to you from geometry, complementary and supplementary angles. So hopefully it's familiar to you. You may kind of confuse the two right now. They might be a little rusty, so let's clear this up. What would make two positive angles complementary? Well, they would have to have a sum of 90 degrees. Now in radians, that's a sum of pi over 2, because pi over 2 in radians is the same as 90 in degrees. What would make two positive angles supplementary? You probably remember that's the sum of 180 degrees. And in radians, that's the sum of pi. Okay, now the examples they give us are in radians. So, because radians are a little new for us, I'm going to look at an example with you as far as what you did in geometry when you found complementary angles. So we're just going to step to the side over here just a little bit. Going to move off to the side. So let's say you had a 41-degree angle and you wanted the complement. Well, you would take and you would subtract 90 minus 41. And so when you subtracted, you would get the difference. So 90 minus 41 would give you 90 minus 40, 40, wait, oh gosh. So 90 minus 40 gives you 50. So why can I not think? 9. Wait. No. Okay, sorry, I got distracted for a minute. So 90 minus 41, sorry, would give me 49. So the complement would be 49 degrees. If you wanted, complement, I'm sorry, I spelled that with an I. How about now supplement? So the supplement would be where I would take 180 and subtract 41. And so we would look at the difference between that. So that would be 139 degrees. So the way that we find the complement and the supplement would be to take the sum, which has to be 90, and subtract the difference. So in degrees, you've done that in geometry, but now we're going to look at doing it with radians. So back to pi over 3. So if possible, find the complement and supplement of the angle. So I'm going to shrink this way down and just get this out of the way. Over here. Okay. So pi over 3. Well, I'm going to take pi over 2 to find, okay, first I'm going to find the complement, which means I want to know what plus pi over 3 adds up to pi over 2. So I'm going to take pi over 2 and subtract pi over 3. Well, I have to find a common denominator, which would be 6. So this is going to be 3 pi over 6 minus 2 pi over 6, which is pi over 6. So pi over 6 would be our complement. To find the supplement, okay, so to find the supplement, this is where we look at the difference between 180, or pi, and we're going to subtract pi over 3. So pi is the same as 3 pi over 3 minus pi over 3 is 2 pi over 3. So the complement would be pi over 6, and the supplement would be 2 pi over 3. So together, pi over 3 and pi over 6 give you pi over 2, and 2 pi over 3 and pi over 3 give you 3 pi over 3, or pi. So let's look at B, 4 pi over 7. So I would encourage you now to stop the video and try to do this one on your own, and then turn it back on and see if you did it right. Okay, so 4 pi over 7. we're going to take 4 pi over 7 and we're going to subtract it from, from pi over 2. So first of all, complement. I'm going to take pi over 2 and subtract 4 pi over 7. Well, I need to get a common denominator. So 14 would be my common denominator. So this would turn into 7 pi over 14 and minus 8 pi over 14. Now watch closely. This may never have happened to you before in geometry. 7 pi over 14 minus 8 pi over 14 is a negative pi over 14. So what does that mean? There isn't one. Because this is bigger than pi over 2. So if the angle itself is larger than 90 degrees, or pi over 2, it's not going to have a complement. And that's where we get the negative angle. And so we know that there is no complement. But 7 pi over 7 would be pi, so we know that it has a supplement. So let's go find the supplement. So the supplement is where I would take pi and subtract 4 pi over 7. Well, pi is the same as 7 pi over 7 minus 4 pi over 7. Again, the same concept as if I were using degrees, 180 minus a degree measure. And so that leaves me with 3 pi over 7, and that's my supplement. Okay. And the last part, maybe your favorite, we get to use the calculator, using the calculator. So in finding the value of a trig function for an angle that's in degrees, your calculator should definitely be in degree mode. When finding the value of a trig function in radians, you need to make sure your calculator is in radian mode. And this is something you need to practice. You'll feel very silly when you don't have it in the right mode and you get the wrong answer. So please, please, please be careful. So we're going to find the value of the following trig functions using your calculator. So as we do these, I would really suggest pausing the video and making sure that you can do them yourself. So the sine of 138, make sure that you are in degree mode and just type that in. To the nearest thousandth, you should get 0.669. Now, while you're in degree mode, let's jump over to C, the cotangent of 421. So still in degree mode, but there is no button for cotangent. So we're going to do 1 divided by its reciprocal function. Remember that cotangent can also be expressed as 1 over the tangent. So we're going to do 1 divided by the tangent of 421 degrees. And to the nearest thousandth, that is 0.554. Okay, now we're going to switch to radian mode. So the cosine of 2 pi over 5. So use that pi key and do the cosine of 2 pi divided by 5. Make sure that's all in parentheses. And that should give you 0.309. And then D, again in radian mode, 7 pi over 3. The cosecant, there is no button for cosecant, but that is the reciprocal function for sine. So we're going to do 1 divided by the sine of 7 pi over 3. And that should give us 1.155 as a final answer. Okay, so that takes us through 4-2. Good luck, guys.